keeping an eye on the chat and questions on both YouTube and on Purpose. You don't need to, it's being live streamed, so it's automatically recording.
I think you might have been muted.
No, my computer's muted because the phone isn't. My computer is muted because the phone isn't. So anyway, we are live on YouTube. Okay. And welcome everyone. We're so glad to have everyone with us today for our live from LPSC 2023. This is at least the 5th, maybe 10th one we've done. And so we have a marvelous group of people here with us today who've been attending LPSC this year. And first thing that I'd like to do is invite each of you to share just a tiny bit about yourselves so that everyone who's joining us knows a little bit about you. Yeah, that slide right there. So Paul, can I have you go ahead and start by introducing yourself a little bit, who you are, what you do?
Yeah, sure. My name's Paul Abel. I'm the chief scientist for small body exploration at NASA Johnson Space Center. Basically, my main interest is in near Earth asteroids, science, exploration, mining, but also planetary defense. So that's basically what I do.
Thank you so much. Seti, would you mind going next?
Yes, I'm Seti Bogart. I am an undergrad at the University of Colorado Boulder. I study geophysics and astronomy. This past summer, I had the opportunity to intern at the LPI. I worked with Dr. Alan Treeman on the distribution and volume of impact melt on the Cleopatra crater on Venus. And then this is my first LPSC, so it's really exciting. And I'm also an LPSC ambassador, so.
Thank you so much. And thank you for being here too. Matt.
So my name is Matt Weller. I am a postdoctoral researcher at LPI. I am a geophysicist by trade. I look at the interior to surface evolution of planets, including the atmosphere. So I take a profile almost straight down. This is not my first LPSC. I've been here for a while. Yeah, and that's me.
Thanks, Matt. And Serena.
Yes, I'm Serena Diniega. I'm a scientist at the Jet Propulsion Laboratory, and I study present-day activity on the surfaces of other planets, especially Mars, and that's what I've been presenting on. Myself and my postdoc have been presenting on at this LPSC. And it is not my first LPSC. I was in Seti's place in 2003, where wow. LPSC was my first professional conference. I am mid-proof.
Thank you. And thank you all so much for being here. So the first question is, can you please say one thing in particular this year that you've enjoyed hearing, doing, seeing, either exciting science, something about this conference this year that you've enjoyed that you wanted to let people know what it's like to attend this conference? Who would like to go first?
I'll go ahead and start. So this is my first big conference since COVID started. And I arrived on Tuesday just in time for the Tuesday poster session because I had a poster up and I walked into that hall and got hit with a wave of noise and almost walked out again. So I was like, wow, I'd forgotten what it was like to be around this many people. But at the same time, I'm looking around at all the faces and seeing all these colleagues that I haven't seen other than on a computer screen, perhaps haven't seen it all for the last few years. And that's been very exciting to reconnect with people. And, you know, we've certainly been doing science and talking about science over the last few years, but it is very exciting to be able to see people in person and to do that. And I hope that the virtual participants are also getting a good experience with this meeting.
Thank you. Thank you so much.
Yeah, I mean, I'll just pile on what Serena said. It's been so great just to see people again in person. I mean, we've interacted a lot, but it's always two-dimensional. It's really good to see people in 3D, and it's such an interactive and dynamic space to be here, right? There's quick science that is done, and you can really get some good ideas and interact with your colleagues that you may have not had a chance to interact with in person for a number of years because of COVID. So I'm really excited to be here at LPSC. It's by far the best planetary science meeting in the world. And it's just something that I always get invigorated after, you know, like I come in and I think, well, I'm going to do one or two projects. And then I'm like, oh, I have 15 projects I'd like to do. I now have to pick down and down select. So yeah, it's just tremendous to be here.
Yeah, I'd agree. Meeting people and just interacting. I had the chance to meet one of the Apollo 17 astronauts yesterday. That was really cool. And just like seeing all like the scientists, I see people walking around and I'm like, oh, I've read their paper, you know? So it's pretty amazing to just like see people and hear about all the amazing science everyone's doing. Yeah.
Yeah, and I can jump in on that too. And it's the energy of being present, you know, walking into a talk, seeing something interesting, walking out, seeing a colleague and having that conversation. The conversation that we haven't been having because of COVID, you know, and it's making the connections, it's making the collaborations that have come out of just some fundamentally great science. And it's so great to, I've started calling it 3D printing conferences. We're all here 3D printed. Yeah, and it's great. The energy is just fantastic.
Fabulous, fabulous. So we're going to continue with some questions, but first, maybe let's find a little bit about those who are online with us at Zoom right now. And so to do that, we're going to do a poll. Let me launch the poll here. So we'd like to know a little bit more about all of you. Let us know a little bit more about who you are or what you think about planetary science. So we've got some questions here for those on the Zoom. The questions that you can't see include things like, I really love space and or space science. I know a fair amount about planetary missions. I don't know much, but I'd like to know more. I find some of it a little bit confusing. Does anybody in this room sometimes find some of it a little confusing?
Oh, yes.
I'm involved in planetary science because we may actually have some planetary scientists or planetary engineers, planetary researchers online with us as part of this. And so we're going to give people about 5 more seconds to go ahead and they can click as many of these as they want. We're going to give them about 5 more seconds just to find out a little bit more about who's on with us. And 4, 3, 2, 1, and it's kind of a mix, right? But most people that are on with us really love space science, and some of them know a fair amount. So we're glad to have all of you here with us. Throughout this, you are welcome to go ahead and post questions in the Q&A or in the chat if it gets confusing. But if the chat gets a little busy, the Q&A is a safer place for us to find the questions. For those of you who are online on YouTube, you're also welcome to post questions on YouTube. We'll try to keep an eye on that as well. So many of you, you're each involved in different types of planetary science. There's so many different types, right? So I wanted to let you share a little bit about some of the research that you heard this year that you're particularly excited in, new ideas, new theories, new research. And one of the things that I was particularly interested in, of course, is DART and the DART results. And Paul, you've been involved in that. Do you want to say anything about all of that?
I mean, for those of you online who haven't heard about DART, feel free to Google DART. Just like DART, you throw a dart, D-A-R-T. It stands for Double Asteroid Redirection Test. It was humanity's first planetary defense test mission, where we, on purpose, ran a spacecraft into an asteroid to prove that we could deflect an asteroid. In case we saw something dangerous coming at us, we wanted to be able to be ready, right? You want to be able to be prepared to defend the planet. And so that's what we did. And, you know, I will tell you, it's a tremendous mission. I've worked on other spacecraft missions. I'll just tell you this little funny bit from my perspective. This is the first mission where I really wanted to lose telemetry and lose that signal from the spacecraft, right? Because that means we actually hit the asteroid. All the other times when we work on spacecraft missions, we want that data, we want that telemetry as long as possible. But this is the first time in my career that we wanted to make sure that we hit, and then of course the spacecraft was destroyed. But it was a tremendous result. We actually proved that we could deflect the asteroid. We hit 160 meter diameter asteroid called Dimorphos. And we changed the orbit period around the primary asteroid called Didymos by 33 minutes, which was tremendous. And we think that we were so effective, not only from the momentum of DART running into the space of the asteroid Dimorphos, but it was the ejecta, all the bits that were thrown off from that impact added that extra push. That's why we got such a large change. We were hoping for maybe 7 minutes if we just ran in, but we got that extra couple of factor of 2 or 3 because of the ejecta thrown off. So it was a really tremendous, and of course, some of those results was all presented on Monday, and it was just tremendous to see that. So it was, Monday was DART day, so.
So, Seti, was there anything this year, you've been, you're still learning here.
Yeah.
at LPSC. Was there anything that caught your eye that you really enjoyed hearing about this year?
I may be a little bit biased, but definitely Venus for sure. I think the news about the active volcanism was pretty cool. And then I'm also really excited about the upcoming Venus missions in the next decade. Hopefully they'll be like right in time for me. So and so I'm excited about those.
Thank you.
Yeah.
Awesome. Matt.
Well, I've also been living and breathing Venus. So I've been sitting there in the sessions. Venus is extremely hot right now. But besides Venus, I've been living InSight, and the InSight session has been phenomenal. The data we're getting back about the interior of Mars is just, it's amazing. We are able to indirectly through seismic waves image the interior, figure out the size of the core, figure out what the interior structure of the planet is. It's just, it is absolutely phenomenal, and it is going to open completely new avenues of research for Martian science.
Fabulous. Thank you, Matt. Serena, how about you? Is there anything particular that really, really caught you this year?
So this is some very preliminary results, and there's still a lot of questions around it, but I study frost on Mars, especially the carbon dioxide frost. But one of the rovers, Perseverance, they did a campaign to actually see if they could see frost in their area, and that would be probably water frost. And so in that case, it was interesting what they presented on. This is the difficulty with conferences. You write your abstract and then you finish the campaign and then you find out what your results are. Meteorological information, so they have information about the atmosphere, the humidity and temperature and such, predicted that they should be able to see frost. And then they did it, they checked the composition with one of their instruments and did not find frost. And so this is now questions about their methodology, exactly what, whether or not they made the right assumptions about the frost point, at which point water frost should have formed. Maybe there were salts in the area. Or is it telling us something about the water vapor distribution, because the humidity sensor is 1.5 meters above the ground, and then they're looking for frost on the ground. And so they made assumptions about how that water vapor would be distributed, and maybe those assumptions are incorrect. So again, very preliminary. There were more questions than answers in that presentation, but as someone who's actively trying to understand where does frost form, what types of frost are found, because that tells us something about how these water and carbon dioxide are moving around on Mars. It tells us about the atmospheric dynamics. It tells us about the subsurface, how much vapor might be there. I thought that was pretty interesting, and I'll be looking for those future results as they work it out.
Awesome. Thank you. Well, we've got a number of questions already, so let's go ahead and let's tackle just a few of them. So let's start off. Venus is only a little bit smaller and less dense than Earth, but it's only 80% of the mass of our planet. Does anybody want to tackle that?
Starting with the easy question.
Okay.
Well, I mean, that is an unknown. Turns out that the growth of planets in the solar system is probably a stochastic process by just impactors coming in and aggregation of material. And Venus might have just had less large impacts than the Earth, and it's slightly smaller. It might have formed in a slightly different part of the disk that had a little bit less rocky material. But that range is, I mean, there's just a range of formation scenarios for planets, and you can have quite a different range of sizes as a result.
Awesome. Paul, there's a question about DART here about, the debris cloud, and is it going to be a hazard to deep space navigation? The debris cloud from the DART mission, where it went and what happened to it.
Yeah, couple of things about the debris cloud that we got from DART. So this is another thing where it's really important to have friends along with you on the mission. So international collaboration is really fantastic. And we wouldn't have gotten these great images of the DART dust cloud in situ from space unless we had that LiCiCube little CubeSat flying with us, right? So we got some really good images of that. Right now, we don't think it's going to be a hazard for anything, to Earth or any deep space navigation or anything like that. What's going to be interesting is to see what we did to Dimorphos and Didymos, because we have Hera, we have our European colleagues sending a mission. It's going to be launching in October of 2024. And it's going to investigate what we did. Right now, are there still going to be pieces flying around that they'll have to, be careful of watching? We don't think so, but who knows? But they're really going to be able to figure out what it is we did to Dimorphos and how much, did we just make a crater? Did we change the shape? Did we do anything to Didymos, the other asteroid that's nearby, right? We didn't hit Didymos, but the debris from Dimorphos, did some of it go onto Didymos? We don't know. And so this is going to be something that's really exciting. But from a hazard perspective, we don't have to worry about that. No.
Awesome.
Yeah.
We've got some other questions about DART, but let's move on to some of the other questions first. Let's see, there was one here about Venus. Any guesses as to how much more energy comes to Venus as electromagnetic energy from the sun than was previously thought? Anyone want to try tackling that?
Maybe not me.
I guess I can. Venus is closer to the sun than the Earth. It gets roughly twice the solar insolation. Venus also has an insulating cloud layer, so it retains a lot of the energy from the sun. So that's one of the reasons why the surface temperature is so high on Venus. That energy comes in, heats things up, and then can't leave. So it's why it's an extreme greenhouse climate. But yeah, it's closer and hotter currently. Yeah.
Awesome. And there's one here about Ceres. So how salty is the Ceres ocean? Is it different from our table salt? Do we know the answer? Serena, do you know anything about that
I
one?
don't study series, unfortunately.
Yeah.
Okay.
I can try and take a stab at it. I think it's going to be quite different than our usual table salt. I would be very surprised if, all the information we have right now is that we think it's a very salty sort of liquid layer that may be kind of mushy. We don't know if it's actually an ocean or not. We know there's something there that's fruiting these types of salts, but I think it's going to be quite different than our regular table salt. I think it's going to be a little bit more different than what we would find here on Earth, but that's the best I could say.
I'm fairly certain if the geologists went, they would still look at.
Oh yeah, no, yeah. And then of course that would cause everybody no end of excitement.
Steady, I've got a question for you.
Okay.
And that is, so this was your first conference.
My first LPSC. I've been
LPSC.
to other ones, but not as big as this one. Yeah.
Was there anything about attending this conference that surprised you in terms of what you were picturing in your head before you got here? As somebody who's new to this conference.
I would say I was probably a little bit nervous before I got here. Yeah, just because it's like my first big in-person conference and just, I don't know, meeting all these like scientists and stuff. And so, yeah, but everyone's been really nice. So for everyone's like always willing to talk and share, what they're studying and what they're working on. And the scientist to student interactions have been really great as well. So, yeah.
Have the rest of you observed? I think there's quite a few early career and students at this conference on a regular basis, and I'm really, really pleased to see students. Have any of you ever told a student, I don't have time to talk to you, I don't want to talk to you?
No, never.
Never.
Have. I think that's one of the things that's, I love about the conference, right? Because you have a chance to interact with colleagues that and you've worked with for many years, but you also have a chance to work with people that you've never met and also the up and coming early career people that are coming in the field, right? And I think that that's part of the excitement and the infusion of new ideas and that energy, I think, is really, really important. So yeah, no, I never turn anybody away. I always talk to them.
So, thank you. Let's see. So there's one here about Magellan data showing active volcanoes on Venus. That's one of those big stories that came out of this conference, right? Does anyone want to speak to that one a little bit? Seti, do you have any thoughts? Were you in that session? Do you like Venus?
you were in the session.
You like
I was in the session. To be honest, I don't know what answer I would give to that question. I may not have that extensive.
So, and for everybody who's watching, the entire question is this kind of lava flow enough to explain the resurfacing of Venus that's been observed, or is the supervolcano global resurfacing hypothesis still considered? Matt, do you have anything you want to add to that or speak to that? Yeah, do you want to talk a little bit about what came out of that session and what they're saying?
Yeah, so did you want to take a stab at that first?
It was they found volcanic vents, I think, which are signs of active volcanism on Venus. I think it was Magellan data that was taken about 30 years ago.
Yep.
That did that. And so, yeah, that was basically the gist of it. Yeah.
Yeah, so yeah, they looked at repeat passes of the Magellan data, different look angles. And so the Magellan data or craft had 3 orbits where they imaged the planet, and they got progressively less coverage each time. But they started looking at the differences, and they found one of the vents looked like it had a flow coming out of it. It was deformed, and there was what appeared to be a new flow. The vent is, I don't actually want to put numbers on it because I don't remember. The vent's large compared to the Earth, but small compared to what's on Venus. So it's actually a very, very small flow, but detectable. It might be something like 20 kilometers across, something like that. I definitely don't quote me. I know it's recorded, but that's always dangerous to pull numbers out like that. But that flow itself is very, very small. So it wouldn't be enough to explain global resurfacing. And that's still very much an open question, but we do know the resurfacing would happen through lava flows and volcanic events.
So a related question, the new upcoming Venus missions, if any of you know, will they be able to detect the same sort of changes if they're happening at that point?
Yes, Envision and Veritas actually are designed with that in mind. And they're nominally they're supposed to fly at enough of a separation that they could see activity between the missions.
Very cool.
Yeah, that's the idea.
And let's see, there's one here about Mars InSight data. And asking, will it help to refine our theories on what the early Martian environments and possible habitability was like? Does anyone want to take a stab at that? Or maybe even just explain a little bit more about what InSight is, for those who don't know.
Insight person.
Yeah. Basically, InSight is a mission that was flown that has a high precision seismometer on it, and it's designed to detect Mars quakes to see how active the planet is currently. And with the seismic waves, you can actually infer something about the materials it goes through. So core structure, mantle structure, lithosphere crust structure. It's useful for the current state of the planet. It's a really great image of the current state of the planet, but it's not enough on its own to say what's happened in the past. So that mission isn't, but the rovers are actually much better, looking for evidence of fluvial activity and the craters and deposition. Those are much better at determining the possibility of past habitability.
Cool, excellent. And let's go back to DART. So one of the questions about DART was how the results might be different from the models.
Yeah, well, it's, from our expectations, when you prepare for DART, we were thinking about DART and the impact, right? When you have the momentum transferred from the spacecraft into the asteroid, it's always we hope it's going to be at least one, right? A factor of one, right? So you get that momentum transferred. But what we didn't know is how we would get enhancement from that ejecta, right? All that material that was thrown off. And our models ranged, from like 1 up to maybe a factor of 7 in difference, right? So we really didn't know exactly what was going to happen, right? That's why we did the experiment. That's why we did this mission. And we actually find from our analysis of the ground-based and plus the space-based observations of DART and the in situ observations from LICHI Cube, we find that's about 3.6, roughly, give or take. There's some uncertainty on that. That's why Hera is going to go there and help us out, refine that number. But we think it's a factor of about 3.6. So what that actually tells you is this is the kinetic impact deflection method is something that could be very efficient if we see something coming at us and we have time to send a mission out there and ram it into it and deflect it off course.
Thank you. And then there's one here about Venus's atmosphere, roughly 100 times denser, makes terminal velocity reduces terminal velocity. And so wanted to know more about the expected impact speed of Da Vinci. Does anyone know anything about that?
I have never done that calculation.
I don't know, but as someone who studies present day activity on surfaces, I really hope the impact velocity is not that high because I want those surface observations.
Yeah. Awesome. Okay. And there's a question from YouTube. So what are the skills that you use most? And I expect it might depend on what you're doing from day to day, but can you think of some skills that you use as a planetary scientist? Communication, working with each other, collaboration, calculations, how much time do you spend in front of your computer by yourself versus working with others versus.
I think I'll start, and it's not so much of a skill, but it's being open to new ideas, right? And being able to take inputs and brainstorm, and being aware that we have some ideas of what may happen with the experiments or spacecraft or what we expect, but being open to those new ideas. There's been many missions where we've gone and all of a sudden we get to a particular asteroid, or we get to a particular planet like Ceres or Mars, and all of a sudden we see something that's actually really, really surprising. So we have to be prepared to, adjust our hypothesis based on the data, right? So being open to new ideas, being open to new ways of thinking and addressing the problems so we can ask the right questions later on to get to the science, that's sort of a skill that I think many of us use. And it's one of those things we just learn over time, right? So yeah, that's the skill that I would say is number one. Yeah.
Awesome. Sadie, do you want to go next?
Sure. I think for me as just like a student and like as an intern, I think there's been a lot of reading more than I expected. Just like reading and researching and talking to people about it. I think there's a lot goes into doing that before even like starting the project that you're working on, just understanding the basics and the fundamentals of those. And so, yeah, that's what I would probably say.
A lot of reading initially rather than just jumping into
yeah,
calculations
exactly.
and programs.
Yeah.
Okay, awesome. Matt, what do you think?
Oh, so many. Tenacity is one. You have to, things are not going to go the way you think they're going to go. No matter what it is. The easiest projects are often the hardest. Things that are unexpected crop up and you could give up and try something else, or dig in and just keep trying to understand it. Multitasking for the same reason. You have to be able to juggle many different ideas, many different projects at the same time. And probably the most important one that goes with both those, time management, because you do have a finite number of hours to work. And if you're too tenacious, you dig in too far on something and you're letting other things drop. So you have to balance all of those.
Awesome. Serena.
Yeah, so one of the big areas that skills that I practice regularly, both in my science as well as in my mission work, I also work on the Europa Clipper, is finding connections between things and translating between people and ideas. There's a big part of that in the area I work in for science, the present day activity. It's very interdisciplinary. I look at the geomorphology, that's kind of my area, geomorphology being looking at the shape and sizes of things on the surface of the planet. But that leads to questions about the environment. So I have to go and understand the atmospheric dynamics, and I have to understand the chemistry of the surface and all of these other things. And then that leads to collaboration, because I cannot be the expert in all of these places, but I can find people who are, and we find those connections, and you ask the questions that help you figure out what the connections are. And then you find the people who can help with that. And that's one of the things I love about planetary science is you mentioned how much time I spend in front of my computer by myself versus working with others. I spend a lot of time in front of the computer by myself, but the science and the main results all involve meetings with people and reading papers that others, you can build off their experiences and results. And there's so much building with other people that I really enjoy that about planetary science.
Absolutely.
And I want to add one more thing. I think also just being able to communicate what you're doing to not just people outside your field, but people outside of science in general. I think because if you don't know how to communicate what you're working on, then it's like, what's the point? So I think knowing how to deliver the stuff that you're researching on is a big one as well.
And jumping off of that a little bit, it's storytelling.
Yeah.
Ultimately, there's always a story. Missions are flown to tell a story. You're asking a question about something and you're trying to flesh it out. And there's always a narrative.
Indeed.
Was there much discussion this year about the Europa Clipper? There's so much excitement around it. People can't wait for it to be ready and out there, and we're gonna have to wait years, but
Yeah, so it's launching next October. And so we are gearing up for that. I wasn't in the Europa sessions, unfortunately. I was at the Mars sessions at this conference. This is one of the issues that come with these large conferences. Is the sessions are run in parallel, and you have to pick your favorite topic for that, your favorite child for that particular afternoon that you're going to pay attention to. And then there's the discussions with colleagues, right? So you're working all that out, time management. But yeah, Europa Clipper, a lot of excitement there. The instruments are getting delivered and the spacecraft is coming together. There is a YouTube channel that you can probably Google up where you can watch the Clipper as it is being built in the high bay. And that is super exciting. It's really fun. And I think on Tuesdays, they do live questions for a couple of hours.
nice.
So I recommend folks, if you're interested in the Clipper mission, check that one out.
And going off of picking your favorite child, I was definitely one of those people bouncing from room to room just to catch all the talks that I wanted to go to. So
See, I'm mid-career now, so I'm like, I'm gonna sit here and listen to all of the talks because I'm not moving.
So for Venus exploration, what are your thoughts on the NASA, is it pronounced HAVOC? HAVOC mission to explore the atmosphere instead of the surface? I'm not familiar with that one.
Yeah, I'm familiar with I know of Da Vinci and Envision and Veritas.
So this
So,
one,
sorry.
one that's early on in, must be one that's early on, or maybe it's an instrument or something.
Yeah, I'm not familiar with it. Yeah.
Okay, sorry, we don't know about that one right now. It's not so far along down the pike as some of the others probably, so. And let's see here. There's a great one here about, okay, can a PhD research scientist submit a NASA ROSES proposal where the proposer is the only PI on the proposal submission?
I believe you can, however, it has to go in through an institution. So the people do not submit proposals, institutions do. But you can certainly have a one-person research team.
You could do that, but that's going to be, I think, difficult. You'd have to, because usually it's a team of people are on a proposal. It is possible. It's possible to do, but usually it's done by teamwork or colleagues, I've seen it in small teams, but yeah, it's possible. It is possible.
As with all proposals, you do just have to establish that you have the skills and resources available within your team, whether it's one person or many, to answer the question that you have proposed to answer.
Right.
And Serena, there's one here for you about Mars, the winds of Mars. They're much less dramatic than in the Martian, but it has planet-wide storms. What explains sort of the planet-wide sandstorms? Can you?
It's a very good question, Daniel. So the winds on Mars are definitely not as dramatic as in the Martian. That is something the author of the Martian has fully admitted to. He needed a reason for them to get off the planet. The winds can blow very strongly, very fast on Mars, but because the atmosphere is so thin, it's not very strong. And this has been one of the questions then that has been asked, separate from the Martian, is how do you move sand and dust on Mars? We know we can kind of use Earth-based models and predict what wind velocities may be needed to move it. And then you look at the rover data and the winds don't seem to get that strong. There was some interesting work by Jasper Koch, 2010 and 11 papers, which looked at the way in which the lower gravity and the lower atmospheric density changed the way in which the wind interacted with the surface. So it's the same physics, but you need the higher winds to get the sand off the ground, but you need lower wind velocities to keep it moving once it's going. So on the Earth, those two velocities are about the same. On Mars, once you get a good gust, you can get stuff moving, and then the lower winds are sufficient to keep it moving. And so you can get that saltation. And that was really important because it helped address that question. We see ripples, we see dunes, we know wind is moving sand around. How are the winds high enough? Now, and then you get to dust, and that's a different question. There still is an open question of, we know dust gets off the ground. We see these massive dust storms. That's what you're referring to planet-wide. That would be a dust storm instead of a sandstorm. Has big implications for operations on the surface. Dust devils probably get dust off the ground, and InSight saw a lot of vortices, but not a lot of dust devils, which is why it also unfortunately died.
Yeah.
Because the dust covered the surface and wasn't lifted off by dust devils and things. We know sand moving can help move dust, but we don't know exactly how that all works and at what rates. What are the dominant means by getting dust off the ground? So actually, the other thing I presented on at LPSC is I'm working with a group of people who are pushing the ideas of in situ measurements of these active processes with small missions. And dust lofting on Mars is one of the concepts that we're working on, of put a small package that is dedicated toward observe the activity as it's happening and get that wind, humidity, electrostatic measurements along with the dust and the sand motion. So you can really match that together and build those models, which would allow us to better understand what's happening on Mars and make those predictions about how dust gets off, whether it's a small dust devil or going up into a planet-wide storm.
And yeah, I just wanted to add on about InSight. The really neat thing about the InSight mission is the seismometer was so sensitive that it was actually responding to wind. So the seismometer was picking up wind speed and variation. So they were getting a lot of data from that.
It was really good for the atmospheric scientists. We were very excited.
Awesome. Okay. Did anyone visit any of the sessions about the moon, the lunar sessions? And we can't leave the moon out. Does anyone want to say anything about the moon?
I did not attend it.
I
didn't.
Sorry.
I'll just throw in, we know that there's a lot going on with the moon in general. I'm not up on the latest lunar science, but the PRISM calls and the missions, they're going to be NASA sending payloads
Yeah.
to the surface of the moon. I think over the next year, the first ones are launching. So there's not only been a lot of good lunar science from LRO and such, but we're looking for that in situ measurements.
Yeah, and
Pretty
then,
fun.
and stay tuned, we're ramping up for Artemis. I think we're gonna see shortly here in a few weeks, the crew announced for Artemis 2, the second mission, which is the orbital mission around the moon and back. And then not too long after that, we're going to be starting on Artemis 3, where we actually start thinking about landing on the South Pole. So it's a very exciting time. I work in Johnson Space Center, and a lot of my colleagues who are engineers and scientists there are really, really excited about the prospects. And of course, people in my building are super excited because we're going to bring samples back. So we're going to have more samples to look at and analyze and tease out all those scientific questions from the moon and particularly the South Pole and all the volatiles that may be contained within them. So it's an exciting time.
I was talking with a couple of early career scientists about they were examining things like lunar soil simulant in growing plants and whether worms would work with the soil and help to make it all sorts of really interesting things. So some of those conversations that you have in the hallway or at lunch with different people and what they're doing. Okay, so let's see here. I'm trying to read this one. What do you think of the new idea introduced originally, the electrical processes in the heliosphere might play out an important role in planetary auroras and surface formation processes? So none of the folks here are heliophysicists. We do have some who deal with space weather and interactions with planetary surfaces, but I don't know if anyone here would. The majority of the people at this conference are planetary geologists, with some exceptions, several exceptions this year, but.
I'll take that question and just turn it into a question that I can give a small answer to, is pointing out that the solar cycles are really important, the solar wind for tying into planetary atmospheric evolution. So that's one thing that Maven found of the orbit around Mars, and tying back to the dust. This is one reason it's so important to understand the dust on Mars, is when we had that planet-wide dust storm, there was an increase in water loss because it was getting up high enough and then being stripped by the solar wind. And so this is where all of this ties together, right? We can understand the present day surface processes. That may tell us, go back to the habitability question, it may tell us something about even ancient Mars and how Mars lost all of its water, and how these seasonal and yearly cycles, which are what's observable now, but you integrate that over billions of years, and you're getting back to the planetary evolution and ancient habitability questions. So it's all very interconnected, and it makes it super frustrating and really interesting to try to solve these questions.
It forces us to talk to each other.
It does. It does.
Because these are so interconnected.
And one of the things I will say that, when we're dealing with the sun and in reference to some of the spacecraft missions we've done around small bodies, the gravitational field is so low that actually the solar radiation pressure plays a big part in how you operate your spacecraft, right? There's some places where if you're not too close to the object, the solar radiation pressure dominates the motion or the effect. You don't have as much effect on the gravity because you're in a microgravity environment, but that solar radiation pressure really makes a big difference. Related to DART, one of the things we saw why this solar radiation is really important is it's helping make that long, nice tail that you see in these images, right? All that material that is blown off, it's sort of followed in DART's orbit, but it's being pushed. And so the lighter particles, the dust, is more responsive to solar radiation pressure, and that gets pushed out further. The bigger blocks, we're talking centimeter scale, maybe a bit bigger, they respond more slowly, right? So that's why you get that nice gradual tail. And eventually that tail will, when all that material is pushed away or moves away from the system, that'll just disconnect. And that's why we see the tail slowly fading over time.
Cool. Is that related to, there was a question here about visible filaments. Is that of any relationship to that?
It's a little bit different. So the visible filaments, that's basically, we think, a result of the impact on the Dimorphos surface. Dimorphos, if you look at it, it looks like there's a huge jumble of rocks that have just been together. It's actually a rubble pile, right? We don't know for certain what's underneath the surface. But we see these meter scale boulders. We don't see any fine dust material that we see on some of the other asteroids. And so DART hitting that surface, you have concentrations of pulverized material and boulders and blocks all moving out. And some of you get this clumpy nature. So that's what causes those filaments. These rays, if you think about impact craters on the moon, you see these nice big impact craters, but they have rays that go out, and that's a concentration of that sort of ejected that debris. And that's what we're sort of seeing with DART, but it's in space and, you know, very dramatic. And so slightly different because we're not in a major gravitational field. We're in a microgravity environment. So that's what you're starting to see there.
Serena, there was a question here about budgets for missions, I think. And I was wondering, so, you know, let me see if I can find that one. Did I lose it? It's at the top. How large are typical budget reserves? And none of you were in charge of NASA's budget, but you know, for handling unexpected new discoveries. Did you want to tackle that one a little bit?
I definitely don't have an answer for that specifically. At the stage of mission that Clipper is at, there are budget reserves, but it's, you know, we're pre-launch. So it's for the instrument development, and as with everything else, right, as you're building individual instruments and as you're trying to integrate them into a spacecraft to make sure everything works together, there are issues and questions and challenges that come up. Something doesn't test the way you expect, or there's an unexpected interaction between an instrument and another instrument, and so it has to be worked out. So there's certainly, NASA holds, when they put these missions together, there are budget reserves that are put in for that. Once you get past launch, one of the strategies that we're using for Clipper, it's not so much a budget reserve, but we're trying to build a operational scheme, an observation plan that has some room in it for flexibility, right? We have to show to NASA that we can achieve the science that we said we're going to achieve. But that's with what we know about Europa now. We're going to get there and get data that's like 100 times better than what we've had before in terms of resolution, and new instruments that haven't even flown past Europa before. And so in the operational scheme, you try to build in some flexibility. So we get there and we find the plume, or we see the whale, or, you know, whatever it is we find at Europa, and that, you know, that there's enough room that we can pivot what we're doing and have communications in place for having the science team as a whole have that conversation and say, okay, if we're going to make this change, what does that impact? Does that impact our ability to ask this other question, which is more important? So there's a lot of that discussion and prioritization, and it's a team effort because you have all these different experts with these different science questions that they're focused on, but they're all really important for understanding Europa. So it's going to be really exciting once we get there. Those first images, those first couple of flybys, everyone is. Yep. We know we have an idea of what we want to see and what we're hoping to see, and then but nature always throws a curveball, and it usually leads to something even more exciting.
I will add that a lot of the times it's like what Serena said is absolutely right. You know, it's really hard to build in the extra money for the unexplained surprises. You have that built in the mission anyway, where you're trying to cover all your bases. But most of it is because of unforeseen things that within the engineering and building of the spacecraft. But we do have a way of, you know, for example, have a mission and we've discovered some new stuff, and we do the prime mission, and then we have opportunities to delve into more of the questions, right? And we have more time. So we go for extended mission opportunities. And so these are things like, for example, I'll give OSIRIS-REx. OSIRIS-REx is coming back. It's going to drop off its sample this September. We're super excited, get that sample back from Bennu. But it's going on, right? It's been extended. It's extended mission because we know there's another asteroid coming by in 2029 called Apophis. So OSIRIS-REx has been extended. So to take advantage of that opportunity. So it's not exactly what the question was asked, but it gives us some flexibility at NASA to utilize good spacecraft. There's a good scientific question that they can answer, and then we can keep doing that. So that's one of the things that we have a little bit of flexibility in helping us answer more questions.
Mm-hmm.
Thank you. Thank you. So we're starting to run out of time. We've got a little bit of time left. I'd like each of you to answer the one here about which of the talks that you attended made you think or say, wow.
Good well or bad well?
I don't know. For me, aside the active volcanism on Venus. I would say the ones on Mars sample return. I think that's pretty exciting, and just to think that, I don't know, in about a decade, I think it's 2033 or so, in about a decade, we could have the Martian samples here. I think that that's really cool. And just seeing the plan for it and the outline and all the talks that have been given they've been really cool. Yeah.
I think for me, I'm a little bit biased because of course the DART is such an amazing thing, but one of the things is the fact that we hit it. And of course we didn't know what Dimorphos was like beforehand, right? It was far too small to see or have an idea of what it was like. So we got up close and personal, and it looks like it's a rubble pile, but what makes me go wow is the fact, the range of possibilities, depending on the internal physical properties of the asteroid. Did we make a crater, right? Is there a crater there? Is a crater that we're going to recognize, or is it going to be just like a divot? Or did we really reshape the entire asteroid? We didn't destroy it. We know it's still there. but did we reshape it? Is it in a new shape? And what is Hera when Hera comes and arrives, launches in 2024? It's going to get there late 2026, early 2027. What is it going to see? So that's what made me think like, wow, oh my God, there's lots of possibilities out there that we have yet to learn.
It was a tough question, Matt, Serena. Either of you have one that you can think of?
I think for me, it would be the InSight mission talk. About from concept to launch to data acquisition, and it was given as the Brzezowski lecture, Mazursky, however you pronounce it. I'm not even sure. Mazursky, yeah. The inside story, the inside jokes. It is concept, birth, life, death of the mission. And it's not wow as in this is super exciting science per se, which there was, but it was wow, this is the concept that was taken. And for me, I thought that was the most wow moment.
I enjoyed hearing a few talks at this conference that was involving data science techniques. So this is one of the areas that I've been getting into. That was my presentation today, is we've been using machine learning and data science techniques to do broad surveys across several Mars data sets to detect frost on Mars, so we can form a nice global map. And hearing about those techniques being used by others to map out pitted terrain, the Swiss cheese on Mars, and identify craters and things like that. It's really interesting to see that these techniques that have been used in the astronomy and the earth sciences community, in planetary science, we actually have enough data to be applying them, because you run out of intern time at some point. Interns are great, but they can only map so many things. And to see these techniques coming out and the types of investigations, you kind of need that first manual study to identify what the question is and what the model is that you want to use. But then you want to do that broad survey and really understand, where does this happen and where does it not happen, to further constrain it and test the hypotheses. And that's where these data science techniques come in. And hearing about those and seeing that increase over the last decade or so in the number of talks that involve those concepts, I think is very interesting. So if any of you out there are working in data science, there is also a path for you, definitely, in planetary science.
And just going off of like machine learning, I know I went to one talk about using machine learning to map the chaos terrain on Europa. I thought that was really cool.
Yes.
Yeah.
And I think we have time for at least one more. So let's see, there's one here about your dream data set, sample, or observation. If you could take any observations or data sets or samples, what would it be? And I see everybody.
I know.
Yeah, I know exactly. I'll go. Yes, Venus sample return. Venus sample return.
I agree.
So rocks from the surface of Venus, or
On
you
the
talking
surface.
core or?
No, surface.
Surface.
Yeah, tessera and planes.
Okay.
Yeah, it would tell us more about Venus than almost every other mission we've run to date to the planet.
Okay, cool. Serena, you look excited too.
Yes, I want the lander on the polar region of Mars that will sit there for an entire Mars year and monitor the environment and the formation of that seasonal frost and how the dust interacts with it and how the grains in the frost sinter, forming the translucent ice slabs, and then the jets that come up as it sublimes. Like, watch all of that with a microphone, cameras, the whole just like watch that whole process because it's so not Earth. This is an environment where ice goes straight to gas and it's energetic and it drives activity, and we know it's happening. And we found all this evidence of it. Actually watching that happen, that would be very cool.
So Seti, you agreed with Matt. Is that your sample, or is there something else that you wanted to add?
No, I think that the sample, I would go with that as well. Yeah. Yeah.
Piece off the surface of Venus.
On the surface of Venus.
I mean, there's so many. I mean, oh my gosh, like trying to pick, it's like, you get one wish. What do what is it? This is like this.
It's like
So,
choosing your favorite.
yeah, exactly. Choosing your favorite child. For me, I guess if you had to, pin me down and say, come on, Paul, make a decision, I would say what I'm most looking forward to, what I would like the most, and it's a mission that's ongoing. We've been advocating it for years, is the data from the NEO Surveyor mission, right? It's going to find a lot of the near-Earth asteroids that are out there, but it also finds, main belt asteroids, it finds comets. It's actually a really foundational asset that we have that will help us understand what's in our backyard, right? And what asteroids out there that are dangerous, what asteroids out there are really interesting from a science standpoint, and what other targets are there for visiting with spacecraft, right? So all of that's what I'm super excited about. But there's so many. I mean, I could go on, and we could be here all night.
Definitely.
Okay, so the final thing, rather than, I know that there's still lots and lots of questions, but we're not going to answer everyone's questions about the solar system tonight, folks. Sorry about that. There's so many great questions out there. Is there something that any of you have? I'd like each to think a little bit about something you'd like to say. It can be about any of the things we've talked about, something we haven't talked about, something about careers, something about what it's like to be a planetary scientist, something about attending conferences and why the role that conferences play, any conference plays in being a scientist, any of those things. I'm going to let you each have something to say. And that's, I know that's really broad. I didn't want to confine you. So I'm going to let you each think just for a few seconds about anything you'd like to say, because we've only got 3 minutes left. So.
Real quick, my favorite color is cobalt blue. But besides that, no, seriously. I think one of the things that I would like to say is I love my job, right? It's like I'm not working because I get to do exploration and I get to see new worlds for the first time that very few people get to do. And I get paid to do it. And it's truly amazing. And it's just going into work every day, there's always something new and different. The wonder of discovery, and then just trying to figure out, oh my gosh, we really don't know that much. And it's like I'm going to school every day. Like I haven't stopped going to school. So it's an amazing job, and I'm very, very lucky to do what I do.
So, yeah. Well, from the questions, I can tell there's like already experienced people here, but if there's like any like college students or anything in the audience, I would say definitely put yourself out there and just apply for as many opportunities as you can, starting with the LPI internship. I don't know. I just think it's crazy just to think about, like, just a couple of months ago, I was just starting the LPI internship, and then now here I am at LPSC, and it's all been wonderful. So yeah, just put yourself out there and just go for every opportunity that, comes your way, because it's a really, really interesting field to be in, for sure.
If I can follow this study, what I was going to point out is for anyone looking to get into this field, internships, because they're still open for NASA and JPL and such. So do check those out. And there's also citizen science projects out there. These are ways that you can get into it. Get your hands dirty with some of the science, do actual science, and see whether or not this is the field for you.
Yeah, and kind of on top of that, don't be afraid to, you have a question, something interests you, reach out. We love talking about our science to people. We love outreach. We love engaging. Ask us, we will talk to you.
And we have, I'm going to try to open the final closing poll, and we also have a slide with some more information about many different things. So we'd like all of you who attended, we'd love to have your feedback on today. And let me see if I can figure out what I'm doing here. Go ahead and let's share, not that one. The poll is live. Awesome. I'm trying to share the slide and I'm running into a few problems, but that's probably that one.
Sure.
Share. I think that it's receiving. Okay. The thing is, it's actually showing under that slide there or something weird like that. It's just.
Mhm.
So, everyone, please join me in thanking all of our panelists for tonight. We're really delighted to have them. It's been a busy conference and it's not over. There's a poster session that they need to be going to. So join me in thanking them. And for all of you who joined us tonight, we're really so happy and thankful that you joined us as well. Have a great evening, everyone. Have a great conference, and thank you all.
Thank you. Thank you.
Righty, so. And hold there. Stop sharing. And we're going to remove the spotlight and remove the